show that the harmonic series, so that's the series n equals 1 to infinity, 1 over n, is divergent. So again, this isn't a geometric series. Not everything is a geometric series, so I can't use my formulas here. And I'm going to have to look at the partial sums, okay? But I'm going to do it in kind of a tricky way. Let's start with S sub 2 first. S2. So 1 plus 1/2. I add up the first two terms in this series. And now I'm going to jump to looking at S4. 1 plus 1/2 plus 1/3 plus 1/4. And notice that this is going to be greater than, greater than 1 plus 1/2 plus 1/4 plus 1/4. That's because 1/3 is bigger than 1/4. And if you simplify this now, you have a fourth plus a fourth. It's 2/4 or 1/2 plus 1/2. So I'm getting 2 over 2. So S4 is greater than 1 plus 2 over 2. And then S8, 1 plus 1/2 plus 1/3 plus 1/4 plus, this is going to get not so nice, 1/5 plus 1/6 plus 1/7 plus 1/8. So this is going to be bigger than 1 plus 1/2. We've already said this 1/3 plus 1/4 is bigger than 1/4 plus 1/4. And then this over here is going to be bigger than 1/8 plus 1/8 plus 1/8 plus 1/8. So let's add up all those fractions. 1 plus, so 1/2. And then in the 1/4 plus 1/4, that's also 1/2. 1/8 plus 1/8 plus 1/8 plus 1/8, that's 4 over 8s are also a half. So it looks like I have 3 halves. So let's take a moment and look at this, what's going on. S2 was equal to 1 plus 1/2. S4 is greater than 1 plus 2 over 2, and S8 was 1 plus 3 over 2. So I took 2, 4, and 8. 2 is 2 to the first, 4 is 2 squared, 8 is 2 cubed, all right? So I took powers of 2 in my partial sums. And it's giving me these nice bounds here. It's not a formula, but what I just learned is that S sub 2 to the nth power is bigger than 1 plus n over 2. There's this pattern going on. And that might be helpful for us to notice. So let's just take the limit of this lower bound here, the limit 1 plus n over 2. What's that limit equal to? 1 plus n over 2. The limit of 1 is 1. What about n over 2? infinity. So I'm getting infinity here, right? And these partial sums are bigger than this 1 plus n over 2, and that goes to infinity. So this tells me that those partial sums also have to go to infinity. So the limit of s to the sub 2n is also infinity as well. This means that my partial sums can't converge. This means that the sequence S sub n diverges, and when your sequence of partial sums diverge, your series diverges. Okay? So the series 1 over n diverges. Yes.
So I understand what we did on the last part. But
the first part?
Yeah, I'm totally lost.
Yeah, so in general what you want to do is you want a formula for S sub n, right? Because like on the last problem, we wanted a formula for S sub n and we took a limit. But for this problem you can't do that. You can't find a formula for S sub n.
Because it's harmonic?
Because it's this harmonic series. I'm adding these fractions together, and so if you try to create a formula for S sub n, you're going to struggle. You can't do it. And so instead, because I want to show that it diverges, what I do is I create a lower bound for these partial sums.
Why not an upper bound?
Because I want to show that the lower bound goes to infinity, and so my sequence of partial sums also has to go to infinity. Something smaller goes to infinity, so the bigger thing has to go to infinity as well. Okay?
What about the grouping
The inequalities. So this just came out of there being a pattern. There was someone who noticed, okay, if I look at powers of 2, I can see this relationship going on. So with S2, I got 1 plus 1/2. S4, which is 2 squared, its lower bound, or sorry, yeah, lower bound was 1 plus 2 over 2. And S8, which is 2 cubed, is greater than 1 plus 3 over 2. So the power of 2 is getting your numerator for your fraction. So S of 2n is greater than 1 plus n over 2. So it might help if I write here. If I write, this is S2 cubed. This is S2 squared. So notice that the power that appears here matches what's there. The power that appears here matches what's here.
So it's n over 2.
Yeah. So it's really just out of this desire. We have something, we want to show diverges. We can't find a formula for the partial sums. So instead I create this lower bound and show that that goes to infinity. So the bigger thing has to go to infinity as well. Yeah. Yep.
So adding all those fractions just to prove that the whole S of 2 cubed exists.
It was just to establish, yeah, this formula right here. Yeah. Or really it's not a formula because there's not an equal to. It's to establish that inequality.
So like how did you get all those
numbers?
How many did you know like to do that?
To do?
Yeah.
I didn't come up with this. Someone came up with it. It's in your book.
Oh, okay.
But someone noticed a pattern that was happening.
Oh,
Yeah.
okay. That was...
Yeah, like how do you come up with this? I'm not claiming that I came up with this at all. It's something, yeah, something somebody noticed and wrote down and then got shared with all of us. Okay? Okay. But now, the whole point of the story was for us to learn that the harmonic series, the 1 over n, diverges. It's just difficult to show it. There was this kind of, not necessarily convoluted, but an alternate pathway to showing that it diverged, okay?
So would this mean that most harmonic series is going to diverge anyway?
Well, there's only one harmonic series. It's just 1 over n. It's not like the geometric series where you have a whole bunch of them depending upon your value of r and a. Here, the harmonic series is just one series. It's 1 over n. That's it.